Okay, people who are joining this live stream, this is a working session with some time that I get to actually think about the content of our physics project. And Jonathan is hopefully here with me, and we were thinking about various experimental implications of our models. And we looked a few days ago at the question of the early universe and its potential decay from an infinite dimensional hypergraph to a, well, in the end, three-dimensional one. And so we had as a toy model of that, we were looking at taking a graph, like a torus graph, and randomly removing, just randomly removing, what were we removing? We're removing nodes from that graph, right?
No,
Right.
we were removing edges, and we weren't. It wasn't from a torus; it was from a manifold graph, not a maximally non-torus graph.
Wait a minute. We started off our graph called GI5. Okay, I understand. Okay, so that was supposed to be a five-dimensional graph from a flat five-dimensional manifold, and then that. So that's our initial graph, and then destroy graph just removed edges. And what we observed was that we have this strange phenomenon, which we only partially understood, about jumps down in dimension.
What do you mean we only partially understood? Which part do you think we didn't understand?
Oh, actually, right. So the final understanding was the jumps down are due to pieces of the universe breaking off.
Well, no, that wasn't true.
Okay, what was true? What was true?
You don't need hypergraph disconnection. You can make do. You only need kind of local disconnection in the sense that you need the thing to be no longer accessible within a geodesic ball of a certain radius. That's not the same as disconnection.
Okay, so let me understand that. So you say, I mean, these are directed hypergraphs. So you say the one-way streets don't let you get there. Is that the point?
No.
Okay, then explain.
It's really simple what's going on. So you've got, you're computing the Hausdorff dimension just using ball of fixed radius, or actually a collection of spheres of increasing radii. And then you are removing edges. And if you remove edges from the interior of the sphere, particularly on the, in the lower shells, the dimension will increase, right? Because you are increasing the growth rate and therefore the exponent, and that's what the dimension is. That's why you see these local increases.
Yep.
Then occasionally what will happen is you make the graph sufficiently sparse that a particular vertex is no longer reachable within that radius. That's not the same as disconnection, right? Lying outside the bound of some sphere is not the same as being disconnected.
So you're claiming that the outer shell is no longer that you are basically connected by a thread to that outer shell. So roughly what we're talking about is if we draw kind of the cartoon version of this, right? So we're talking about some okay, so let's write down what we're saying here. Okay, so we're talking about kind of the major effects. And one effect is the effective dimension increases. Okay, so as major effects as edges are removed. Effective dimension can increase because the fraction of edges in the interior of a geodesic ball because removing a fixed fraction of edges has more effect on the interior of a geodesic ball than the exterior. Do you agree?
Well, that's that's why the increases occur more frequently. It's not why the increases happen. The increases happen simply as a consequence of the more you remove from the interior shells, the faster the growth, the higher the growth rate.
So wait a minute. Okay, so here, let me understand that. Maybe we can do an example of this.
What is there to understand? This is what I'm not getting, right? So you've got, okay, we have a function and we're approximating it by an exponential.
Mm-hmm.
And I'm going to just reduce the value of that function at certain places. If I reduce the value of the function towards the zero, the exponent is going to, the exponent of my approximation will increase. If I reduce the value of the function,
I understand the claim. I understand the claim. Right. I'm just trying to be careful about, because
what is the this is what I need to understand. What is the analytic problem that you are anticipating?
The problem that I'm anticipating, okay, I'm not really anticipating a problem with this. I'm anticipating, as you remove things in one place, you're concentrating on one point, right? And you're saying, this is, so I mean, if we were to draw this, let me just take a specific example. Let's say it's dimension 1, right? So what we have is, range 10 or something. That represents the number of nodes that we get at particular distances in this geodesic ball, right? So it's pretty obvious then. Actually, it's not obvious in this case. I mean, if I take my favorite example of the grid graph, my favorite, and I start from the center of the grid graph, and I imagine removing edges here, right? Then it will be the case that the fractional effect on the number of edges, on the number of nodes reachable, will be highest in the interior relative to the exterior. And therefore, let's just think about that for a second. Is that really obviously correct?
Like I say, I can't tell if this is intentional. You're confusing two different things, right? There's the question of why the increases occur, and then there's the question of why the increases are prevalent. I thought we were discussing why the increases occur.
Well, no, I was trying to discuss why they're prevalent. Right. Okay, in other words, why it's common for it to be the case.
Obviously, why they're prevalent is even easier. That's just because if you have a function that's reasonably approximable with an exponential, and you randomly sample weighted by that function, you're more likely to sample towards the right-hand side of the curve than towards the left-hand side of the curve, i.e., towards the exterior than the interior.
Well, you're saying, but where the sampling, the amount of no, I don't think that's quite right. I think look, the basic effect here is.
How is that not right? What's not right?
Because I don't think it has to do with, look, the issue is, which thing are you sampling? Are you sampling the center point of the geodesic ball, or what are you sampling?
What do you mean? We're sampling edges. We're removing edges.
Okay, okay. You use sampling in two different senses. One question is when you compute the dimension, right? You're doing that by starting from, let's say you compute the dimension around a particular point. You start from that point, you're asking how many nodes do you reach at a given radius around that point. So all I'm saying is it's pretty obvious. This is sort of okay, so question. In percolation theory, one doesn't usually look at, for percolation clusters, which is essentially the kind of thing we're doing here, actually, this is very confusing to me. Let me think about this for a second. When you do percolation theory, you certainly look at the dimension of percolation clusters, but the only time when that's interesting and when people really consider it is at the critical point where you get this kind of nested structure of bigger and smaller pieces of the percolation cluster. What we're talking about here is you're changing the probabilities here, and you're asking a different question, which is I think, let me think about this for a second. What is the relationship between looking at this and the There's a question from Gupta on our live stream asking a question: how does the Hausdorff dimension evolve as we randomly delete edges? Yes, that is the simple question that we're asking right now. You asked a question about Hamiltonian evolution. This is this is a much lower level formalism than standard quantum mechanics. So all the stuff with Hamiltonians emerges, but it is not what you start from. Okay. In any case, let's talk about where we're trying to get to here. So the first question is, I mean,
we
the
know
argument for what
we're trying to develop you want to develop a continuum theory of dimension change on the basis of large classes of hypergraph rules.
That's correct. That's the objective. The objective is, what is the analog insofar as Einstein's equations represent a sort of bulk statement about the change of curvature? The question is, what is the bulk statement about the change of dimension?
Right, exactly.
Okay, so
what's the problem with the analysis we've done so far?
Was done a few days ago, and I need to refresh my memory about what was going on, and then we can develop some momentum to go further and also check that we got it actually right. I mean, what we observed previously was that most of the time, so I'm trying to remember what was the difference between these cases where you didn't see jumps and the cases where you did see jumps. There were cases where you see a gradual increase of effective dimension followed by a decrease as you delete more edges. And there are cases where that occurs in jumps. What were the differences between those cases?
Well, gradual decreases were for small volumes of, the place where there's no discontinuities whatsoever was for a trivial volume element, as you can see from the parameters of the function.
So
clearly, if you're looking at neighborhood graphs of radius 1, this effect will not exist. There's no distinction between the interior and the exterior.
Okay. Okay. So the claim would be that the typical case.
Look, I mean, the monotonically decreasing case is the one where you have a neighborhood graph of radius 1.
1, right? Which is not very interesting.
It's also obvious.
So this is just.
Oh, I thought, but can I clarify what? I still don't have a good handle on what it is that you think is incorrect about the analysis I already did, and that would really help me to understand, to contextualize this conversation.
Well, okay. So let's try and do it more carefully. Okay, let's try and write down
carefully. So we have a monotonically increasing function from 0 to some maximum, m, right?
Mm-hmm.
We're approximating that by an exponential. First question: do you agree that if we reduce the value of the function in, say, the lower half?
Yeah. That standard fitting will give you a higher exponent.
Okay.
Yes.
Second question: do you agree that if we then sample uniformly on the basis of the value of that function, where we're going to reduce its value, then we will tend to preferentially reduce the value, at in the towards m rather than towards 0?
Yes, but I'm not sure that's the relevant thing to think about.
Why is it not the relevant thing to think about?
Because I think one has
in exterior shells than interior shells, because the function is monotonically.
I understand, and so your argument then is that if you randomly zap edges, the chances are you're going to zap edges towards the exterior of the ball. I agree. Is that the argument you were making?
Right. And
okay, fine. But then
what is not correct about that analysis is my.
It's fine. Okay, but then given that analysis, let's try and write down the mean field theory equation for what that implies. Right. So in other words, let's assume that you are randomly removing edges. Let's assume that as a function of some parameter t, let's say, okay, as a function of the fraction. Okay, so the effective mean field theory. So let's assume that there's a fraction, I don't know, f, let's say, fraction f of edges have been removed. Okay, then I want to know what is our estimate for what that does to the effective dimension d. Right, so in other words, we're trying to figure out what is this curve, right? Is there an envelope for this curve, and is it the case that we have these discrete jumps, but what is the continuum theory of what's going on here? Right? For sufficiently large network, what is the theory of what's going on? Okay. So how to think about that? So as we say, with your argument, if we remove a fraction f of edges, then basically our whatever we call it, our geodesic ball volume. Let's assume the geodesic ball volume initially goes like r to the d. Then what you're saying is, if we remove a fraction f of edges, then so the reason this is a little bit tricky is because this is a discrete thing. So normally you would just say the amount of volume is just r to the d over f, but that's not correct here. That's not the relevant thing, right? So do you understand what I'm asking? I'm asking, what is this? Go ahead.
Yeah, I think we agree on the objective.
Okay, so now how do we do it? So we're removing a fraction f of edges, and what does that do, given that the original approximate geodesic ball volume was r to the d? What do we think, how do we approximate that removal of edges? So in some sense, given that geodesic ball volume, that means that there are, from the original node, there are approximately r to the d geodesics whose endpoint is the exterior of the ball. Do you agree? It's kind of the definition of the ball volume. Do you agree?
No.
Okay. What do you think is correct then?
Because there are degeneracies.
Well, there are degeneracies. Wait a second. There may be.
It would be for the case of a manifold-like thing, which is kind of what I was proposing we use. But if we use something like a grid graph, then that's obviously not true. There are degeneracies.
Right. There are multiple geodesics that wind up in the same place.
Right. That's kind of what it means to not be a manifold graph.
Okay. But I suspect that's going to be significant to us. Okay, so assume.
Of course, we should be
assume it's manifold-like, because that's what's going to give the mean field theory, is a case where there isn't degeneracy, I suspect.
Of course, right. As I was saying, I think we shouldn't be using grid graphs and we shouldn't be using torus graphs.
Okay, well, fine, but they help me to understand, to visualize what's happening, okay? And maybe we should use, what's a good example? We could use a random mesh here as an alternative sort of sample graph to understand what we're talking about. So that would be a discretized region of, what can we use here? We can just use a rectangle probably. If that works. Yeah, okay, so there's our alternative, and we could say region mesh. Is that right? Mesh read. Now, what do I want to get? How do I get the mesh out of this? How do I get the graph? There's a way of doing this. What is it called?
Mesh region is a way of doing that.
Of that. What does that do? How do I get the actual graph out?
This is why I created that whole batch of functions, so I didn't have to worry about this stuff. Is there a reason we're not using those?
We can use those. I was just trying to give myself one picture that you wouldn't object to of a thing that is an approximation. Yeah, sure, we can use. How do we use your functions? So resource function of your manifold to, what is it called? Manifold. What is it called?
If you want the flat case, flat manifold to graph.
Okay, and then what do I do?
And then dimension, discretization cutoff, and point count.
Doesn't like that. Up.
You might need a higher discretization threshold. That may be too high.
Okay, that was why I was using the other function, so that we could actually generate. I mean, why can't you use the same heuristics that this thing uses to generate, to determine what the mesh size should be?
Well, because I thought it's important that this thing should have the correct limit.
Okay, but so give me an example where here, what am I doing wrong? I mean, is this, so if I say graph of this, can I get the plane graph out of this?
If you request pure spatial graph or just spatial graph, depending on whether you want it coordinatized or uncoordinatized.
Okay, so let's say spatial graph here. So that's going to be the analog of this. Is that right?
Right.
It's a little odd because this clearly is more uniform in sampling 2D space than this looks to be.
Right.
Even that
right.
these are coordinates. So say it again.
I mean, the more regular it is, the worse approximation to a manifold it is, right?
Why?
Well, because the limit of a regular thing would be a grid graph.
I know, but I don't think this has that regularity issue. This certainly doesn't have the degeneracy issue. If I look at geodesics inside this thing, we will not find degeneracies.
Or you'll find fewer.
Yes. But I don't understand why this clumping. I mean, so
you want a sampling process, you want a uniform sampling process where you can prove that in the limit as the density goes to infinity, the set of degeneracies forms a Lebesgue measure zero subset, which you can do in the case of this approach. I don't know if there's
okay. So how is it? So just to understand, I mean, one thing that's coming. I'm now already. Gosh, I'm losing my mind. Which version? Spatial point process and so on. This is the Is that in the new version? Am I completely losing my mind? I'm just losing track of which version exists and which version doesn't exist yet. And I thought spatial statistics was already, yeah, okay, it is. Spatial point process is already there. Okay, so I don't think this is completely irrelevant to what we're talking about here. This is, so this is laying down, this is, right? This is, for example, laying down points in 2 dimensions that are random, but have a certain, are never closer than a certain radius, for example. How is that in your case? What are you doing? How can you describe the statistics of where the points are?
Well, in this case, I mean, it's a uniform. I mean, the way these all work is that you're uniform sampling, but where the sampling is based on the expansion of the Riemannian volume element around the
But
point.
it's flat in this case.
Right.
So this should be uniform sampled.
Well, they're all uniform sampled.
So if I were to take, random point, a rectangle, and I don't know, 200 points here, and let's say graphics of this. What did I do wrong? Oh, okay, so the claim is that the statistics of this random sampling are the same as the statistics of this random sampling. Is that right? Those are uniformly sampled points in a region.
Yes, sure.
Okay, so for example, if we were to measure one of these things like let's see, which one is it? Isn't there some correlation function? What on earth is this? There's a correlation function. I don't quite understand. Oh, here we go. Mean point density, and then there are these various nearest neighbor G, the probability of finding another point within a distance G of a point G of R. So if I say nearest neighbor G of, I have to remember how this works. Okay. Not sure why we have to give it the region. Oh, I see, within that region. All right, so that's going to give us statistics of these points within this region, which is something not completely unrelated to the geodesic ball question, except that in this particular case, it's simply asking, let's see, what is the definition of this? Gives the probability of finding another point within a distance r of a given point. Okay, so slightly different. Okay, but anyway, okay, so the objective here is if we remove a fraction f of points in one of these things, and we claim it's not going to matter ultimately what the discretization scheme is, so long as it is and so on, then how do we estimate in a situation like this? We're trying to estimate how the volume decreases. So maybe one thing we could look at is to get us some intuition about what's going on. In a case like this, what are the actual graphs that we're getting, right? And we should see in that case, what does destroy graph X do here? It says, okay, so which one are we using here? We're using destroy graph XX. Let's take that. I mean, so I'm asking, if we take that thing.
Right, the intermediate percolations. But again, I don't understand the previous analysis that I did. I don't understand the thing that you think has been missed.
I'm not sure anything's been missed. I'm just trying to do it more carefully, just because I'm just so that we can get out what we don't have yet is a mean field theory approximation for this quantity. That is, as you know, remove.
It's obvious how to get that.
I'm sorry.
I mean, if the analysis is correct, then it's obvious how to get that because
okay,
it's just put on the Riemannian volume element.
Percolation theory does not usually consider geodesic balls of this type. Just doesn't. That's not what it looks at. I mean, there is.
I know, which is why I'm not suggesting we use percolation theory.
Right, but so then my question is, the ultimate result here is, there will be some result for d of f, right? The dimension as a function of fraction of edges that have been removed, and d of f has some functional form, which we can kind of guess from looking at these pictures, but we don't yet know what it is.
Right. And as I say, I think as long as one accepts this analysis, it's obvious how to derive it. Is it not?
Somewhat. But I just want to check the analysis before we go and try and derive something.
Percolation theory in the Riemannian volume element.
No, because percolation theory is mostly obsessed with what happens around the critical density.
I know.
Right, but so ordinary percolation theory,
which is why we shouldn't use percolation theory. Right,
but it has almost no information about this. So the question is, how do you derive this?
Yeah, so we should do perturbation theory on the Riemannian volume element.
Why do you think perturbation theory will be enough? I mean, your claim is that as a locally around a particular value of f, you're saying we should be able to work out essentially a something that is analogous to some kind of
all we're doing is we're deforming the metric so that the volume on interior spheres becomes lower than the volume on exterior spheres by a greater factor than it was previously. Right, that's what happens when we remove edges.
I know, but it would be nice if we get a more direct derivation that didn't go through that essentially assumption about what's happening. In other words, if we could just say directly from the graph, which I bet we can, go directly from the graph and just say, given that we have a graph with a certain dimension here, as we remove edges, I'm pretty certain that there's going to be just some, maybe it'll be some differential equation with respect to f, which tells us the incremental change, in your perturbation theory approach, the incremental change as you change to the dimension d, right? And that would be a nice thing to have, because that would tell us, given that we have a graph with a certain dimension and we've got a certain fraction of edges filled in, because clearly for a given fraction, we can get all possible dimensions. The fraction doesn't tell us the dimension, because the dimension is this growth rate. It doesn't care what the underlying, in other words, we can change. The thing that's a bit surprising, okay? Here's the thing that's a bit surprising. If we simply take one of these graphs and we simply decimate it by removing edges, argue why the dimension doesn't stay the same. In other words, what we've done is we've just said, and it clearly doesn't stay quite the same because, but what the most simple-minded thing that we would do is we would say, you know, the most simple-minded thing to imagine is as we remove edges, the distance, the number of edges you have to go through. Well, let me see. If we add edges, we could expect that the typical number of edges you have to go down to get from one point to another is going to go down because there are more paths to get from one point to another. But the issue is, it's not simply a question, you know, if I change the density here, so is your 0.2 basically the density of edges, the fraction of these? So I mean, if I were to do the following thing, if I would take a random graph, and I would, and unfortunately we don't have a random planar graph, do we? And that's something we should get. I think we've talked about that several previous times. It would not be too hard to get a random planar graph, although there may be a bunch of different. Okay, so if I have something like this, right? I've got 200 edges, 100 points. Let's say I go to this. Clearly, I mean, what is the dependence of dimension on the average number of edges? Obvious.
Well, yeah, I thought so, but you.
Okay, well, okay, then go through it. In this case here, the average number of edges is determined by that parameter there, correct?
Well, yes.
Okay, so let's just go through this. So that's the average.
Or not. I mean,
what's that?
I can walk you through the argument, or I can stay silent.
No. Please go through the argument. I mean, this is that's the result for 0.15, right? So are you saying the dimension of these two should be the same or should be different?
Well, obviously, in the limit, they'll be the same.
Okay. All right. So now, why is this different from taking? So why is it different to take this and remove edges versus taking this where it generates it with a different fraction of edges?
Because the discretization scale determines the curvature scale on the curvature balls. Well, I mean, that's what a curvature scale means.
Okay, let's go through that more carefully. Okay, so you're claiming, so the basic point is, you say when you first generate this, you're joining these points with a certain, is that correct? You join this here with a certain probability, assuming that the metric is flat. Is that right?
There's no probability in the joining.
Well, what does this number mean?
The discretization scale, the scale below which points are treated as adjacent.
Okay, let's go through this then. But there's randomness in which point. Okay,
right. There's randomness in the sampling. There's no randomness in the edge generation.
Okay, so by sampling, you mean you pick coordinates for each point, correct?
Yeah, well, we sample points in the manifold, and then we connect them based on metric.
Right, but we can think of that as exactly the same thing we're doing here. We're picking coordinates of points, right?
Well, no, correct. It is exactly the same. Hence why if you call flat manifold a graph and then request points, you will get the same thing as you got below there.
Exactly. Okay, so now what you're saying is, let me just understand, how do you determine whether to join 2 points? So we've got this picture. How do you determine whether to join 2 points or not? You're saying if they lie within Euclidean distance such and such, join the points, is that right?
Well, not in general Euclidean distance, but if you expand the Riemannian volume element at each point and another point lies within that element, up to radius given by the discretization scale, then they're joined by an undirected edge.
Right, but okay, but in this case, we're talking about flat manifolds, so we are talking about Euclidean distance in this case.
Sure, right.
Right. Okay, so just to go through this case, so we make sure we understand it. So you're saying in this case, for any 2 points, let's say these 2 points here, what determines whether those 2 points are joined?
Whether they lie within the distance less than or equal to the discretization scale.
Okay, so if they lie within that distance, then they are joined. True statement?
Yeah, just the same as if you called neighborhood graph of random point 200 with radius 0.15.
Okay, let's do that. No, so nearest neighbor graph of so what we have here is a bunch of random points, and so you're saying let's see, how does it work? Nearest neighbor with
And then
a,
you want infinity, comma, and then the discretization scale.
I think it's all, comma, the discretization scale. Okay, so all, comma, 0.15, for example. Okay, lovely. Okay, so I think we understand this. I understand this at least somewhat now. Okay, so then and the generalization of this would be if this was not, if you were trying to sample in a non-Euclidean space.
Right. The whole point of those functions, rather than using nearest neighborhood graph, is that you want this to work for an arbitrary Riemannian or Lorentzian metric.
Right. So, but could you do that by just defining a different distance function for this nearest neighbor graph?
In principle, yeah. If you just overloaded the distance function, so it took the distance function generate, if it took basically g g mu nu dx mu dx nu.
Right. Okay. All right. Fine. I'm just making sure I understand what's going on. Okay. So then the scheme is, if given your assumption about what the underlying space is, what those coordinates mean, then you're joining points that are within a metric distance, less than something or other, less than your cutoff scale here. Correct?
Yes.
Okay. I'm very slow. Sorry, I know I'm frustrating, but I'm just trying to, okay. So, all right. So then, correctly, it should be the case that with our dimension estimator, that if I just generate, for example, a bunch of graphs here with, a fraction f there, and that fraction f varies from, let's say, I don't know, 0.05 to 0.25 in steps of 0.05, the claim would be, that all of those graphs, if we could, should in principle have the same dimension. Obviously, that one does not, because it's fell apart. But am I correct that the dimension estimator should say all these graphs have dimension 2?
Right. But as I mentioned previously, and as I thought we discussed previously, there's a free parameter in the dimension estimator, which is the minimum maximum, or two free parameters, which are the minimum maximum radii in which you are sampling, right? How far do you expand the volume element?
Yep.
And
right, so yeah.
This whole argument, this whole discussion hinges on the subtlety of whether those parameters co-vary or do not co-vary with the edge density, with the discretization scale. Now, of course, in actual discrete differential geometry, they do co-vary, right? Because the discretization cutoff determines the the characteristic curvature scale, and the characteristic curvature scale is essentially the maximum geodesic ball volume.
Right. Although in flat space, that isn't the issue.
What?
The thing you just described, right? So the curvature scale, you can think of it, I suppose, as fluctuations in curvature, even in flat space.
The curvature scale is the maximum radius of the geodesic balls used in the dimension and curvature estimators. That's kind of what the curvature scale means. Wait
a minute. There can be a continuum curvature that has nothing to do with, which is the thing has nothing to do with sampling. The thing is on the surface of some sphere or something, which has some definite curvature. Right? That's
yeah, obviously in the continuum case, because you can expand the volume element to an infinitesimal radius, the limiting curvature scale is going to be 0.
What limiting? What do you mean by curvature scale now?
I'm using it in the standard, I think the standard discrete differential geometry sense, which is the sense I just gave, right? It's how much what's the maximum, what's the radius cutoff?
Okay, for your estimate of curvature. That's what's that?
Or dimension, the calculations are the same.
Okay, but so you're defining, okay, so then what we're defining is, when we estimate dimension or curvature, otherwise known as geodesic ball volume, and we're fitting geodesic ball volumes,
right,
dimension or curvature, we are basically computing, we are computing what I think I've at various times called V of R, right? which is the volume as a function of distance, as a function of graph distance, right?
We're computing the expansion of the volume element.
Right, but okay, so we can do this with R min to, R min less than R max. Is that what you're saying?
Yeah.
Okay, so those are the scales that you are defining, right? And then we will in general get a different estimate because V of R, if we compute V of R, let's compute, let's see, you've got these nice dimension estimators. How do I use one of your dimension estimators on this? So I want to compute V of R for this thing here, which by the way, I really think is basically the same as this quantity, one of these quantities here, that gives the probability of density of having 2 points at distance R apart. Is that what we want? Yeah. Is it exactly this?
Well, it's the conditional probability. It's you know the position of one point, and you want to know what's the probability of a point existing within a certain radius.
Right, which is a 2-point correlation function, I think.
Right, and from that you can then extrapolate in the continuum limit what the expansion of the Riemannian volume element would be.
Right, but it would be useful to me here to understand what is the okay, so point density, that's different. That's okay, those are density measures. So what we want is, which of these is this? Expected number of points, within a distance R of each point, K of R. Okay, so is that exactly what we want here?
If we want to measure the dimension at a point, yes. If we want to measure the dimension over all points, which is the default for the curvature, for the dimension estimator, then it's the pair correlator.
No, I understand, but I think this is averaging over points.
Well, if you give it all possible points, if you give it a single point, if P data is a singleton set, then it's not.
But where's the data? It has to look, it's getting all the points and it's computing these volumes here, right? And then what this is saying rather uninterestingly, and boy, everything has been discovered in 7 different fields and given 18 different names, because as I understand it, this is essentially the curvature, what we're considering to be the curvature, yes? I think. So, I mean, if we compute, let's see. Oh, I see. One of the problems is that this is in Euclidean distance, whereas what we want here is graph distance. So, sort of it's an analog of Ripley K, for what it's worth, for graph distance. But you've got a function that computes V of R, is that correct? From one of these graphs. Is that true?
I can compute any. You can compute V of R, you can compute D, you can compute R, you can compute mu nu.
Okay, how about we compute V of R? Just for, how do we do that? So I've got this graph here. How do we compute
any of the dimensional curvature estimators can do that as special cases.
Okay. Okay. Which one?
Well, any of them. I mean, Hausdorff dimension, Ricci curvature, Ricci scalar, whatever. If you just request dimension from any of them, it will.
Okay, fine. But what is this the what you're calling Wolfram Hausdorff dimension, which means I should understand it, but probably don't. Okay, so then what? So we take this graph and then what? What do we do here? Just tell me what to type.
Okay, well, yes, you give it a graph object, and you need I don't know what it is you want to compute.
I want to compute V of R as a function of R. So for a given R, I would like to get.
But at a particular vertex or averaged out across all vertices?
No, averaged over all vertices.
Okay, so then you want so graph, and then you want comma all, and then okay, do you want do you want a minimum maximum radius? Do you want what cutoffs do you want, or do you want those to be?
I would prefer them to go from the smallest size to the largest size. So I want to look at the V of R. I mean, I can compute this perfect. Okay, V of R as a function of R, right? Because then we're going to look at how this dimension estimator, because the basic point you're making, okay, if I understand correctly, is what it matters what R min and R max are, because if you fix, as you change the fraction, right, but you fix R min or R max, it's going to mess around with what you assume the dimension is.
Right.
So
yeah.
I just want to see that. I want to see how that would work. Go
vary
ahead.
with discretization scale, then obviously you're going to get these weird effects.
I know, but the effect we're looking for is in the category of a quotes weird effect, because what we're looking for is the variation, something which is not usually looked at, right? We want to know, again, we're trying to compute d of f, the variation of the implied dimension, which is a little bit squiggly because the dimension, as you observe, depends on where we do the fitting over, but presumably in some appropriate continuum limit, it doesn't matter anymore. And I would like to see that.
Absolutely matters. It matters how the dimension, how the discretization scale and the curvature scale co-vary, because otherwise you have no guarantee of commutation between those limits.
Okay.
Right, the continuum. So, what you call a continuum limit is a very, very subtle thing, as I analyzed in great detail in, for instance, the causal set paper. Because what's really going on is you've got two fundamental limits. You've got the limit as the discretization scale goes to 0, and you've got the limit as the curvature, the characteristic curvature scale, which is just the maximum cutoff for the geodesic ball radius, goes to infinity.
Yes, I don't think that right.
You have to vary in a manner that is compatible. Otherwise you don't get commutation of those limits, and therefore this notion of a continuum limit is just not defined.
I suspect that right, there are even more limits than that. I mean, there's a tower of a whole bunch of limits. But the question for us here is,
in the kinematical case, there are only two limits. Those are the two.
Okay, but the question that we have before us here is, in what sense, if we're trying to estimate the dimension of the early universe and how it varies, it might be the case that there is no definition of that without dealing with boundary effects, without dealing with a whole bunch of things that break out of this notion of a continuum dimension, maybe. Or it could be the case that there is you could say, okay, we can't do Friedman, Robertson, Walker cosmology without sort of, there's some sense in which you need the whole universe to do that. If you only take a piece of it and you start sampling pieces of it, it may not make any sense. So the question here is, what is, if we're trying to estimate, so what does it mean? What is the effective dimension? What does it mean? What is the continuum version of that? I mean, a continuum version of that is if you were to measure the inverse square law, if you were to measure Newton's universal law of gravitation, the exponent would be different, right? In d-dimensional space. And so there's a if you're sitting in the early universe, 10 to the minus 40 seconds after the beginning of the universe or something, and you are doing, an experiment on gravity, you would conclude that, the universal law of gravitation was different, the effective dimension of space is different. And the question is there a way in which that quantity, just like you would conclude if you looked at, the expansion of the universe at different stages, you have some standard differential equation that gives you kind of the expansion, the A parameter or something as a function of time. You would, the question is, what's the analog of that for dimension? Does that make sense?
Right. No, we agree, I think, on the objective, and it's a worthwhile one. But
okay, so let's go figure it out. If you have a faster way to figure it out than my incredibly plodding way of figuring it out, great. But I think my objective here was just to understand, in this picture, right, for these very simple graphs, right, I would like to understand how whether we would conclude, because what we've been saying is we can approximate evolution according to this hypergraph update rule. We can approximate it by just deleting edges, right? That was the claim. That was a reasonable approximation. Okay, but this is kind of making that seem a little bit not right, because this is saying in this case it better be true that some version of dimension is unchanged as we change the density of edges, because all of these come from essentially the sampling of a flat two-dimensional manifold.
No, it just means we have to be very, very careful and very precise about the terms we use. So when we talk about measuring dimension, we need to define whether that means measuring with respect to a fixed cutoff or not.
I
As long as
understand.
you find how that cutoff co-varies or does not co-vary with the discretization scale, then it's a perfectly well-defined problem. But until
Okay.
that point, it's pointless to talk about it because it's just not well-defined.
Okay, but then we have to ask the question, in the physical case of the early universe, what is the effective variation of the cutoffs? But it also will be very useful to see.
Because it depends on the observable, right? There will be some, right? What we're measuring, we are never measuring dimension directly, right? We would only ever be measuring dimension via some other observable quantity. It might be effective speed of light. It might be, not inhomogeneities or other kind of.
Well, let's look at these. Okay, so
and presumably these will be associated with different dynamics, effectively, of the of the cutoff scale of the continuum cutoff scale versus the discrete cutoff scale.
So it will be my hope, it may not be true, that there would be universality in this, basically what we're trying to get is a D of T type thing, dimension as a function of some, I don't know what time, what the appropriate time variable is there, but some, that there is some universal formula, just as there is a universal formula for the scale parameter, A of T in a standard. I mean, okay, so let's play the analog of what you just said, right? If we look at some more exotic spacetimes, not something like Friedmann, Robertson, Walker, and we ask, is there a meaningful A of T in those cases? Maybe there isn't. I don't know. In the mixed master universe, is there a meaningful A of T?
Well, there's a scale parameter, but it's not a one parameter family like it is for FLRW, because you don't have the appropriate symmetry.
I understand, but so the question is there, so what you're saying is, if we were to look in a mixed master universe and we were to measure a particular quantity, some correlation function or some such other thing,
right?
Then
it would matter, in mixed master specifically, the whole thing is parameterized by S3, right, rather than S1, which it is for FLRW. So you have a scale factor and you have two continuum shape parameters. And again, the dynamics are completely determined by essentially how these two, how these quantities covary. And if you don't address that question, then it's hard to ask anything sensible.
Right. Okay. So one question is, what is the analog of FLRW for dimension change? Right. So what is the analog? That's the maximum symmetry solution. Presumably, there's a notion of maximum symmetry. What is the analog of maximum symmetry for what we're talking about here? Some kind of isotropy condition. I would think it's basically homogeneity and isotropy. It's just basically the statement all geodesic balls behave the same, independent of where they are. And I don't know what the isotropy condition is. It's basically that all geodesic cylinders behave the same. Does that make sense?
Is this a question or?
Yes, it's a question. I'm asking.
Yeah. Well,
how do we work out the analog?
So isotropy just means that all projections of the Ricci discrete Ricci curvature tensor contribute approximately equally in the limit.
Indeed. But so the question I'm asking is, how do we formulate what is the if we were trying to write down, the objective is, okay, first question is, can we write down, homogeneous isotropic continuum equations? First of all, is there a valid notion of homogeneity and isotropy in this dimension change case? Probably the answer is yes.
Sure, of course there is, and it includes effectively Birkhoff's theorem as a special case. It includes this, all of the standard spherically symmetric, all the spherically symmetric homogeneous solutions of GR are dimensionally homogeneous and isotropic. It's just that there may also be other dimensionally homogeneous and isotropic solutions that are not homogeneous and spherically symmetric in the ordinary GR sense.
Okay, but I mean, you take one of these solutions, right? It has a parameter D, which we know for integer values. We looked at what the for example, what FLRW looks like. I think you had looked at that in your paper, what it looks like when you change the dimension, right? That's what you were looking at with your variable speed of light thing, correct?
Sure. Yeah.
Okay. So again, my question is, can we connect that, again, what we're looking to get is a continuum equation that gives the time evolution of the dimension,
right,
analogous to the way that we get it. Go ahead.
Yeah, we agree on that. That's
okay. All right. So then how do we get there?
Right.
I think what we should do, first of all, is just understand what these cutoffs mean. Because if everything is driven by these cutoffs, right? So what you're saying is, if we look at the dynamics, maybe it's easier to derive what the dynamics of V of R are rather than the dynamics of the derived dimension from V of R. Maybe more obvious what's going on if we look at, as we evolve the system, how does V of R change? So for example, as we prune, edges, if that's what we're doing, V of R it's simply going to, as we prune it, well, let's just look at it. Let's just look at what it does. I mean, that's the easiest way to find out.
We're about to do that, I thought.
Okay, yes, well, let's go ahead and do it.
Right. Okay. So as I understand it, you want no radial cutoff. You want just the default, which is the graph radius,
Yes.
and you want volumes up to all. You want all volumes to be listed explicitly for all vertices. Is that correct?
Mhm.
Right. Okay. So then you want.
I want to average over vertices.
You want to average over vertices.
Well, do you think that's a bad idea because of edge effects?
I don't know. I'm just asking you what you want to do.
I would like best to have something where there aren't edge effects. I mean, if it was a flat toroidal space, that would make me happy. Is that something we can get or not?
Well, yeah.
Okay. Because then we won't have edge effects, right? Then it's reasonable to do the averaging over all points.
Right. Obviously, a toroidal space will be intrinsically flat, but not extrinsically flat.
Yes, but I think that's enough for what we're trying to do here. I think. Maybe not. But I mean, alternatively, see, I'm worried about the edge effects here because I think this thing, particularly as we go to higher dimensions, the exterior nodes here are going to have different V of R than the interior nodes. Right? Okay, let's get it for all. Okay, if we want, let's get the separate V of R's for every one of these.
I'm trying to nail down exactly what it is you want to do. I mean, so if we want a torus graph, we can get a torus graph. You just call extrinsic curved manifold a graph, and you give it the equation of a torus. If you want to
do this one first. Let's do this first, and let's do it separate. The separate V of R's for each of the points here, if that's easy to get.
So then you want all volumes.
And then sorry, wait a minute. The all volumes or the word volumes?
No, you want property name all volumes.
Okay. I don't know. You wrote this function, so I don't know what that is. Go ahead. And then what?
Volumes. And then we want, okay, so vertex method goes to identity. That will return the thing as an association for all vertices. And then you also want volume method goes to identity, and that will return all volumes rather than averaging over them, which would be the default.
Okay, like this, right? Okay, so the graph diameter looks to be about 4, and this, which is really small.
Radius.
Yes, graph radius. Does it surprise you that all these points have up to distance 4?
No, that's how it's configured. It computes the globes as that.
But so let's take an example. So that's
part and parcel of having 4 data points.
Okay.
The boundary effect is huge.
I understand. But so what we get here for this V of R is for every value of R, there is a distribution of values of V of R for that value of R, right? So for each point here, so what we could do here is if we say, let's see. Okay, that's the that's the histogram of the value for each of these cases. You're computing something.
Oh, sorry. Oh, I forgot to mute my microphone. Sorry.
That's all right. Okay. Okay. So you understand what this is, right? So what this should do for every distance r, this gives us the distribution of values of v of r, and we're trying to fit. Okay. I mean, is it obvious to you? Do you have an obvious path forward? Because what I would do here is just start looking at these different cases where we're pruning these things and take a look at what it does as you, but we need something which gives a better approximation to dimension 2 here.
Right. I mean, reducing the discretization scale would be a start. I mean, the approximation is just
by which you mean by reducing the discretization scale, you mean what here? You mean in this case that this scale, go ahead. What?
I mean, reducing taking the discretization scale and making it smaller.
Which in the case of these graphs is taking this quantity here. And so this will be an example of a smaller discretization scale in your definition. Is that correct?
Right.
Okay.
So the graph radius will be larger, which means that the cutoff will be greater, which means the approximation will be better.
All right. Okay. So let's take a look at that. Okay. So like 0.05, we could probably do this with your function as well, but okay. So it's this one here, and that gives us a graph. Why did that have so few things even connected? I mean, so if we go to 400 points, okay, so this thing isn't even connected. So that's a problem, right? It's, in other words, because of discretization, we can end up with infinite graph radius, right? You want larger graph radius, but you don't want to go too far. So what we need is some kind of, what we need is some percolation threshold where the thing, right? We need it to be above the percolation threshold where there is an infinite cluster with probability 1. And I have to say, it's a very long time since I thought about this stuff, but at one point I might have known how percolation theory works on graphs. Do you know that, Jonathan?
No.
Because that's what we need here. Okay, so let's actually compute. I mean, I guess we're computing the number of connected components as a function of, so let's compute. Okay, so let's look at percolation in graphs. Now, of course, the actual universe doesn't, this is just a mean field approximation, so to speak, to the universe. So let's say we have an R scale here, and let's say, okay. I think I've worked this out once before. Seems awfully familiar. Okay, let's do 100 of these. Let's say okay, with cutoff 0.08. Grind, grind, grind. That's interesting. Well, let's see what this is without the histogram. Okay. So there's a single connected cluster in that case. So if we go down to 0.04, oops, that's going to be very connected. Oh my gosh, look at that. Percolation really works. So at 0.04, cool. Okay. So this means there's a definite percolation threshold here. And your claim is that if we look at, okay, so I'd like to look at with R equals 0.08, that's going to give us something where if you compute this quantity here, we would have a larger graph radius, if I'm not mistaken. Does this use parallel kernels to compute this?
No, not natively.
Can I tell it to do that or not?
Not right now. I mean, I can change it to use parallel map.
Okay.
Do you think that's helpful?
I think it might be. Well, let's take a look at this. Okay, so this is now, that's a bit wild. So you understand what this is, right? So we're taking the case close to the percolation threshold. So therefore it is a maximally we're making it so it is connected, but it has the longest graph distance between points while still being connected.
Right.
And now we're computing for every point in that object, we're computing its V of R.
Mm-hmm. Yep,
so what's going on with all of these? What's going on with these things where it suddenly manages to get to the whole space?
Well, those are just vertices that happen to be, uncharacteristically well connected.
Yeah, super spreaders. So do we think that there will continue to be those, or do we think those will be, I mean, are those inevitable, or do we think that those will be, I mean, if we go to a larger, is there an obvious way to get this graph so that we're just seeing density? So we're not plotting all these separate lines. I'm being silly about this. Is there a 2D histogram that we can do for this? So for each value of R, there is a histogram to generate.
Right.
Right? So in a sense, if we computed bin counts for each of those things, we could get the density distribution of this thing. And what should happen is, if we believe there's a meaningful notion of dimension, what should happen is that density distribution should tighten up around something which goes like R to the D. Do you agree?
Yeah.
So in this case here, right? And that's what it means to say that the thing has, is really behaving like a d-dimensional flat space. Makes sense? And then so what would happen in the evolution of the thing, for example, okay, so the question is what this distribution does as time progresses, so to speak. Does that make sense? So I mean, one thing that could happen is that the distribution could, one possibility is we go from a distribution that looks like, basically what we're looking for is something where it goes from one of these to the other one of these, right? That's what it would mean. And the question is, what is it actually going to look like? Because remember, both of these aren't single lines, they're distributions around a line. Make sense? So can we compute what this actually is? So what we want to do is for each value, we want the bin counts. Is that right? Can you see what that's an estimate there. I shouldn't have recomputed it. Okay, so this is now a plot of that. Okay, so now what we want to do is the transpose of estimate. And the first thing we can do is just work out histograms for each of those. Okay. So probably what we want to do here, let me look at this on oops, that's not what I want. What I want is okay. See what I'm doing here?
Yeah.
I mean, I probably want to say here probability. Okay, so what this is doing is it's saying as a function of R, this is looking at in that graph, it's looking at the distribution of sizes of balls out to that radius R, right? Because the question we're asking ourselves is, this picture, right, if we have dimension change, what we should expect to see is that as a function of evolution, we go from one of these to the other one of these, right?
Yeah.
Right, but what we're actually going to see is something where each of these is fuzzed out, where these are merely estimates. They're estimators of this V of R function. And the actual V of R function will evolve in some other way. So one question would be, if we were to look at the actual V of R function, is it easier to see using some essentially kinetic theory like argument how V of R should evolve? Right? Ignore, think about it in some kind of analog of phase space where instead of thinking about, fixed dimension position space in your ordinary phase space, one's looking at some kind of graph phase space where you're asking, where, right, you get what I'm asking?
Yeah.
Do you have a brilliant idea about how to do it?
How to do what? How to do the analysis, or how to
how to compute given V of R for at a given time, right? What we're asking for is as we make, for example, random changes. Let's assume we don't, the rule is just random, right? As we make random changes to the graph, how does that affect the V of R for the graph for a given R? Right. So that's the question. Is there an obvious argument? Because if you were to ask me about the analogous thing in well, actually, here's a question I don't know the answer to. Okay, so in percolation theory, as you change the probability P, let me think about this for a second. As you change the probability P, you're going to change. See, it doesn't compute that stuff. People compute in percolation theory. The thing of greatest interest is right at the critical point, at the critical density. There's the first, infinite cluster, which we also seem to care about, right? The percolating cluster, and that cluster has a bunch of self-similarity, and you can compute its dimension. And let's see, there are critical exponents that determine how the dimension eventually just goes to 2, for example. Yeah, it's sort of interesting that percolation theory is a case where the dimension of the cluster, if you lived in the cluster and you were making various estimates of dimension, you would conclude, with Hausdorff dimension or whatever else you're doing, you would conclude that you're living in a fractional dimensional space, which is very much analogous to our situation. Although I have no idea whether people have tried to do differential geometry on. I looked at this, and there wasn't a lot that had been figured out about things like differential geometry on those kinds of spaces. So I think it's what you figured out is probably what's been figured out there. Okay. Well, in any case, I mean, I'm not sure how much further we're going to be able to get here, but I mean, I would really love to see the evolution of this, right? So this is what this is. This is showing the smearing out of these lines, right? Except that we're not showing in our model here, we're imagining, which I don't understand, okay? This is confusing, okay? Maybe you're not confused, but I am confused. What we're doing is this curve is essentially thicker at the beginning, right, and gets thinner as you go further on in here. I'm actually very confused about what this is doing. I mean, maybe only the first 3 values are meaningful here. Maybe let me just do something slightly different here. Let me look at this up to range of, let's say, at most 200. Help. We have to count it without the thing at the end. But Jonathan, do you understand why I'm confused here? Or you're confused about why I'm confused?
No. I mean, you start off with a sharp peak around 0.3, it smooths out to a shallow peak about what looks about 0.4, and then it reaches, the effective graph radius.
Yes, that's right. But remember, what we're trying to do, we're estimating dimension by computing things like this.
Right. No, we understand what we're trying to do.
Right. So my question is,
isn't this exactly what you would expect? What about what you would expect?
Remember, what we're trying to do, okay, look. The initial thing that we have is, I'm just trying to think how to do this computation. Is this a 2D?
What computation are you trying to do?
I'm trying to make this picture where these histograms have been, where what happens is this curve is.
If you're trying to make that picture from the volume estimators, then that's trivial to do.
No, it's not. Okay, then let me make a slightly different picture. I think I understand what I want to do here. So
I thought I understood what you want to do as well, but I need you to actually state it explicitly rather than just,
Okay, all right. Okay, hold on. Let me see if I can do this. Then maybe.
I thought what you wanted to do was to have a curve for, essentially for the volume element where it's smeared out in both directions as a consequence of the fact that there isn't a unique value of the exponent.
Right? Yes, that's right.
Well, that's easy to do.
Oops, what is this? Hold on a second. What did I just do? Hold on. This estimate here is the value I'm very confused here. Why isn't transpose of the estimate here? Oh, maybe I don't want to say that. There we go. What the heck? Oh, I see. That's kind of weird, actually, because those error bars are supposed to be representing these smearings. I don't understand why the error bars don't look larger here. Do you understand that? The variance of that distribution looks to be a lot bigger than that.
Yeah.
So why are the error bars so small? Right, so I mean, if I say this and I ask for I'm officially confused here. Why are these error bars so small?
I don't know. The variances are pretty much what I would expect from eyeballing that distribution.
Right. So the question is, why does mean around say that the error here is so small? So this thing here, let's say take the second value there. Okay, we got a whole bunch of numbers here. I'm profoundly confused with this. Okay, so mean around. Why is that error estimate so small? Why is that so small? I don't understand. Because let me understand what mean around does. Computes the weighted mean with weights proportional to 1 over delta I squared. Okay, fine. Oh, standard deviation divided by square root of n. Let's see, is that the, okay, so that's why it's so small. Because I see, it's assuming that the thing, I see. Well, it's not completely silly of it, what it's doing. However, it may not be what we want. Yeah, it's not going to give us what we want.
I mean, why aren't we just plotting three curves? One which is the mean, one which is the mean plus, one mean absolute deviation, one minus the mean absolute deviation, or something like that?
We could. I just wanted to get an actual continuous thing, but we can do that. Let's see, how would we do that? We could plot it plus the variance and minus the variance. Standard deviation, rather. Not sure that's the right thing to do. I mean, the thing we really want is to take these histograms on their sides, normalize them, and plot and smear this out by that amount. And I know I've done that computation a zillion times, doing things like that. And you can do it by getting bin counts for each thing. But the thing I'm trying to get intuition for is, as you then change, what's going to happen is, what you might have thought would happen is that a point here, a lump of V of R that was here, would move down here. But that's not what's going to happen, I suspect. I suspect what's going to happen is, in this kind of V of R space, that lump of material, in some sense, that lump in phase space is going to end up moving in some direction here, rather than in this direction here. And so the way that this is going to change is by some dynamic that has to do with the way the estimator works, more so than the direct change of dimension. Does that make sense? Jonathan, did that make sense, or did the?
Well, yeah.
Okay, all right. Do you think you have a way forward here? Because I mean, my way forward is to start making these pictures and trying to understand what this does. Because this seems like the here, I'm going to make this picture.
Yeah, I
So
mean, I suggested the way I would do it. You said you've made these pictures a zillion times, so make one. I mean, if you think that my approach is not good, then do the thing you've done a zillion times.
well, okay, I have to remember how to do it. I thought we actually had a function that did this, but I'm now okay. Hold on, let's think about this for a second. So,
I mean,
what
my
we
view
want,
is this data will be pretty much normally distributed, so we don't lose anything by just doing plus or minus mean absolute deviation. So we might, if we want to build up intuition, we might as well analyze that. But
yeah, okay. So let's say bin counts. I don't understand what this just did. Hold on. Oh, I see. I see. Okay, so we want to go x min x max dx 0, 1000 dx. Okay, and then for each of these, then we can get this by just saying matrix plot. Okay, there we go. Now, okay, that, although it's upside down, is the distribution. Right, that's showing us. So for example, we can say, um, okay, that rather uninspiring thing. Let's put it on a. Oh my gosh, it's a bit weird, but you, I mean, you get the idea. This is showing us as a function of this, showing us both the probability distribution and the, I mean, the height shows us the probability distribution, and the position shows us our supposed quadratic growth function. Make sense? This is the supposed quadratic growth function.
yeah,
Which is not looking particularly quadratic to me, but okay. So then the question is, how does this evolve as we change the f thing? So here, if we go up here, right, so that 0.08. So let's go down here, and let's say we want to compute this thing here as a function of f. That's for a single, I don't think it's going to make much difference. That's a, okay, so we have the transpose of this. And let's say parallel table of that with the 0.08, let's say, going from 0.07, let's say, to 0.1 in steps of 0.01, 0.005. Doesn't really matter, we've got many machines. Okay, so this is going to try to compute, as we increase f, how this curve changes. tell me this thing is not. One of these days, I think in 12.3, this is getting much faster, this launching of kernels. I think it's okay, let's watch this run. So again, okay, let's look at the last one here. That is uninspiringly undifferent. So that's varying this function, this quantity f. I mean, there's a mild difference between these. Right? If we look at the average here, the average is going to be some, estimator of V of R. This is the okay, let's just say show. Okay. So what seems to be happening here, I mean, this distribution is getting broader in this case. I mean, if you really squint, you can see a change from something which looks like it has more second derivative here to something which looks like it might have less second derivative. I don't know if that's actually correct. But yeah. Any other ideas here?
I'm seeing some nicely quadratic stuff for tori.
Okay. So what did you started with a thing without boundary, which I think is a good idea. Okay, help me do this without boundary, because I think it's a much better idea.
Right. So just, as I say, just use extrinsic curved manifold to graph.
Can you do you want to just send me a piece of code?
Okay. I mean, this is a very small one, but you probably want to make it larger if you want to get, very good approximations.
Right. Okay. So how do I make it larger? I change the 600 to a larger number. Yes.
Yes, and you probably want to drop the discretization a bit. Make it, I don't know, 0.3 or something. Okay, that'll be quite dense.
Apparently. Okay, this is obviously very sensitive to these discretization scales, which again, we can compute for each of these things. There's some graph percolation threshold, which we can presumably compute.
Well, I think what ultimately needs to be done is just, as I say, a systematic analysis of the covariance of, radius cutoff versus discretization cutoff. That's nice.
Okay. That's kind of a Swiss cheese torus. Does it surprise you that it has such big voids?
Well, it only has voids in that embedding.
Yeah.
If instead of requesting pure spatial graph as a property, if you just request out the manifold graph, then you can then from that you can extract either the pure spatial graph or the actual spatial graph, which is coordinatized, which will not have those holes.
Right. So this should look like, actually, stop. Well, so this is something that actually has the original XYZ coordinates in it.
Right.
Okay. But then, oh, lovely. Okay. That looks just like our other graphs, except that it is except that everything's arranged on Torus. Terrific. Okay, so let's go back up here.
But the point is that the graph radius of one of these should be quite large.
I know. This is what I was hoping for. Okay. So what we want to do is compute these same quantities for that. Do you agree?
Sure.
Or did you have some different quantity?
Well, I was just computing my stupid thing, which was the plus or minus mean absolute deviation.
Okay. Give me the code to do that. Let's just run that.
No, we can do. You seem to think this is better, so let's do.
Let's do yours because it'll be easier to do because there's a number of things that could go wrong with that code up there, and it has to be tweaked. I mean, it might just work because this code. Okay, let's try it. For example, this, let's see, how big was this? This was 2000. Okay, so this is 0 to 2000 steps of 5, let's say. And this here will be replaced by, actually, we could just replace it with one of these graphs, right? Yeah. What the heck is that?
The disconnected graph, so the automatic graph radius goes to infinity.
Okay. All right, so let's say first, my gosh, why is it running so slow? Okay, first, let's get this out of here. But this may end up getting, I mean, I don't know how far, well, eventually it will get to, yeah, is it obvious to you how far this will go? The graph radius? Do we know the graph radius of this thing?
Well, I mean, unless you compute it, you can't know it. It'll be large.
Right, that's why I was concerned about my code. Because it assumed a certain graph radius. I mean, assumed not too large a graph radius, okay. Okay, so then this is, okay, so that's nice. So up there, what we should be seeing, so this is where we're hitting the edge of the universe, so to speak. But this second derivative there should be characteristic of the dimension that we're looking for here. Do you agree?
Mm-hmm.
Okay, so now the question is, as we evolve this, and by evolve, I mean with the thing we've been we've been looking at is just decimating or not. Okay, so let's take this thing here, and that 0.3 is what's about to change, right? We're going to change the 0.3 to some f here, and then each of those oh, okay, does this look right? Okay, so now I want to also say aspect ratio 1/2. Okay, so now I want to do this for f varying from, for example, what do you think? 0.1 to 0.4? Or what do you think? 0.2 to 0.4? What range of values should we try?
I'm not sure what it is you want to observe.
I want to observe what the variation with f is. So, okay, let's just run these.
Yeah, but
Yeah, what do you think is going to happen? Do you think the curve is going to look the same, but it's just going to change its density, but the spine of it is going to stay the
as
same?
I've said since the beginning, it's really hard to answer this question if it's not well defined.
I know, but this curve has a well-defined form.
No, it
Right?
doesn't, because the extrinsic curved manifold graph is using the graph radius as the default thing. So you're again modifying the discretization scale and then allowing the cutoff scale of the geodesic ball to co-vary in a completely undefined way.
But this isn't, because this is the scale of that geodesic ball in graph radius goes from the smallest to the largest possible radius. Right?
Right. So it's I mean, if what you want to observe is effectively how the graph radius changes with the percolation, with the discretization
Oh,
cutoff.
that's a different issue. That's a different issue. I mean,
It's not, because it's exactly what you're going to observe here. If you don't enforce, basically, we have two quantities that are significant, and you're varying both of them with a relationship that we don't yet fully understand. And my position is you should at least fix one of them if you want to understand how the other one works.
okay.
But
Okay, so okay, all right, we've got definite pictures here. So let's take a look at roughly what happens here. If we can conclude anything from this.
I mean, of course, it's even worse because you're not even using the graph radius. You're using the graph radius of the largest connected component, which is a different quantity again.
Indeed. Indeed. It's the horrors of physics versus mathematics. I mean, okay. So the issue is, I mean, it is kind of, I mean, this is why it's hard to define what this, right? Because you're going to get variation as you change.
Well, it's very easy to define. We fix one of the two quantities.
Yeah, but it's not clear that's what's meaningful. Right? We can obviously we can fix one of these quantities, but the question that we're still addressing is,
what does it mean? I mean, what do you mean by not meaningful? Not meaningful assumes a priori that you have a way of measuring dimension that fixes a geodesic ball radius. If we have that, then of course you're correct. But I'm not aware of any such construction.
sorry, say that again.
What did you mean by when you said it's not clear that's meaningful?
I'm afraid I lost the referent for that.
Okay, so we have these two quantities, right? We have the discretization cutoff and we have the geodesic ball radius cutoff. What is conventionally in differential geometry known as the curvature scale, the characteristic curvature scale.
Mm-hmm.
You are currently co-varying the two with an undefined. I mean, presumably it's possible to determine what the relationship is, but as far as I know, we haven't determined the relationship between the two.
Right, but remember, our overall objective is to figure out in some continuum limit, which we don't understand very well, what I'm expecting is that there is something we can do analogous to what we would do to compute the mean field theory of something which is like a random gas with where you can essentially use kinetic theory to compute, or some generalization of kinetic theory to compute heat equations, diffusion equations, whatever.
Yeah, no, I completely agree. I think such a continuum theory may well exist, but it's hard to derive that unless we define everything that we're talking about.
Well, I'd like to remind you that it is a very fragile thing. I mean, the diffusion equation is reasonably well defined in sort of precise kinetic theory. But when you go to more complicated things like Navier-Stokes, for example, it's not very well defined. That derivation involves various jumps of faith, basically, of limits that nobody really understands. So it's not obvious to me that this is going to work axiomatically. And I think it's going to end up requiring some essentially randomness assumptions. My assumption would be, my hope would be that just as you can say that diffusion, you can give an easy sort of stochastic argument for why diffusion works the way it does. The question is, can we figure out a similar stochastic argument for why dimension change should work in a certain way?
Sure, but okay, correct me if I'm wrong, but it seems to me like with any of these discussions, there are really two sensible ways in which to proceed. Either we start with a rigorous sort of axiomatic mathematical basis, or we start with some robust kind of observational thing that we can compare against. And right now we have neither.
Well, we don't have an observational thing because sadly, we don't really have, incredible visibility into the universe in its first 10 to the minus 20 seconds. So that's off the table. We don't have that. We're doing, what's that?
We have some. We have
very little
measurements and things.
It's from 100,000 years after the beginning of the universe, mostly. I mean,
although the non-Gaussianities and things will presumably had emerged long before the recombination time.
Yes, presumably. But I think that working backwards from that, I don't think we're going to. Well, okay. So a question there.
You don't have observations to compare against, and you're against using an axiomatic method. Then what exactly are we meant to do?
I'm not against using an axiomatic method, except that I don't think sort of the traditional kind of precise mathematical step-by-step is going to get us there, because I think it requires many pieces of mathematics that simply don't exist.
Sure. I mean, there's definitely stuff that has to be developed. But
I mean, the question is, can we make an end run around that by doing something where we essentially do a simulation without having to know, in other words, to develop a full...
What quantity is it that we're computing in those simulations? To compute that, we're having to make an assumption about, what the radius cutoff is.
I understand that. I understand. And the hope is that in some sense, which I do not understand yet, that cutoff, look, the general theory of cutoffs in numerical analysis or anything else is if you've got enough points, it doesn't matter what the cutoff is. And if it does matter what the cutoff is, then there is no continuum theory.
Yeah, but ordinarily in numerical analysis, you're taking a limit with respect to one parameter, which is the number of samples.
Yeah.
We're taking a limit with respect to two parameters. And it's clear that, as I say, how they covary will restrict the situations in which those two limits commute. And if the two limits don't commute, then there is no continuum limit of the theory.
Okay, but look, you should see this phenomenon here, right? You should see the fact that, well, you're saying the way this construction is done, this is already assumed your radius cutoff. But what I would expect to see...
The point I'm making is that there's no consistency in everything you've done so far. There's no consistency in what it is we're actually computing. Because if you look back at the stuff we saw on Thursday, which had these very well-defined, percolation type behaviors, which, I mean, you clearly disagree, but I think it's pretty clear to understand why they occur, right? Why we get sort of local increase followed by occasional discontinuities in which one gets decreased.
No, I think qualitatively I agree. I just would like to understand that. For example, I would like to...
But there we're computing a completely different kind of quantity to the kind of quantity we're computing here, because in that we were fixing the radius.
Fixing what radius?
Fixing the cutoff radius, the characteristic curvature scale.
Really? Why? I mean,
Well, that's why in those graphs earlier, you got the monotonic decrease with radius 1, and you got, less monotonic decrease with radius 3, and so on.
Oh, I see. But this one doesn't have that feature. This one is going over all.
Right, right.
Okay, and this gives this effect here.
Yeah, just like on the, which is the same kind of computation as the one on the left. And the point is that's a different thing, right? Because now we've got an undefined, rather than before where we had a defined relationship between the radius and the discretization cutoff. Now we don't have a defined relationship.
Okay, why don't we see the same kind of phenomenon that we're seeing here? Why don't we see that over here?
Because we're computing a different thing. One of them is one of them's dimension, one of them's volume.
I know, but why don't we see, in this case, this is computing dimension by basically fitting this curve.
Yeah.
Right? So why aren't we seeing, and is it maybe the case that these glitches have something to do with, tail or no tail in these pictures? I'm saying because we're fitting this thing to get this quantity, right? And we're seeing discontinuous changes in that fitted parameter.
Mm-hmm.
So I'm trying to understand why there are those discontinuous changes. And notably, and it may have to do with that connected components business, there is no tail here and there is a tail there.
Right.
And no doubt the presence of that tail will affect the best fit for the exponential increase of this thing.
Right. But as I was trying to say on Thursday and at the beginning, that discontinuity, unless I'm very much mistaken, is a radius-based effect. Right?
Well, yes, in the sense that, look, I'm trying to understand in a broader context what causes that. If the answer is that this thing doesn't have a tail here, it has a tail here, you've chopped off the tail by taking a connected, the largest connected component or some such other thing, I don't know. And this effect here, these jumps here are associated with some change from the way that you're computing, the way that you're deducing from V of R, that you're deducing. The question is, where is the discontinuity? Is the discontinuity already present in V of R, or is it merely present in the fit to V of R that you make? And what's happening, what seems to be happening here is as a function of that parameter, you either do have this tail or don't have the tail. And my guess is that the reason for that is, which we could easily determine, in one case, the presence of that tail is the result of some connected component, which then, in a sense, drops off.
Right. But as I said right at the beginning and on Thursday, it doesn't have to be a connected component. It can
I know, I get it. I'm just saying, look.
Connected, it can just lie outside the radius.
Yes.
If you have a subgraph that is reachable within, distance 3 of a particular vertex, but then you delete one of the intermediate edges, then if the subgraph is still, so the subgraph is now reachable within 4, distance 4 of that vertex, then if your radius cutoff is 3, it will act like a disconnected component. So you'll suddenly see a massive drop off in the volume element, and hence a decrease in the,
But this is the radius. This thing down this axis here is the radius.
I know.
Right. So this is saying, oh, this is very confusing because this thing is on a different scale.
Hold on. So you can see that it's not extending beyond 20 for some of them, but it's extending up to 24 for others. So you're seeing exactly the effect that I said you would see.
Yes, I understand. But I was trying to get a more microscopic version of what we see over here. This is a fit. This is the thing that we are fitting. And yeah. By the way, there's a totally confusing aspect to this, which let me just fix this. Does this work? If I say show this plot range, let's just see. Arrow 120, 400, is that the right way around? I wonder. And then we should wrap up. That's definitively the wrong way around. Okay, color me somewhat confused here. Okay. Well, I have to say, I think that this, this sort of, right. So the reason these estimated dimensions are changing, which is what we've both been saying for ages and ages and ages, is because we're trying to fit something like this and we're sampling different pieces here. But again, I would love to see if there's some kind of way, if we imagine a time parameter. See, again, remember the derivation of the diffusion equation. It relies on essentially a pure probabilistic argument that's based on, you have this configuration space, and you're moving things around randomly in that configuration space, and things can only get somewhere if they were nearby on the step before. And that's sort of the way the derivation of the diffusion equation works. Question is there an analogous derivation here where instead of position of particles, there's some other quantity which is related to the graph that could give you, in a sense, the quotes diffusion of essentially V of R, from which you could then derive the analog, this dimension quantity. Is there a diffusion equation for V of R in effect? And I don't know the answer, but that's I think, well, a little disappointing. I thought we were going to get further here.
Right. I mean, yeah, it's clear what is that with
Well, fair enough. Then we should do it. But what's that?
Is it not clear what to do? I can't tell anymore.
I don't think it's completely clear what to do. I think there's
you just take the Smoluchowski equation derivation of diffusion equation, but you replace the probability distribution with essentially the correlator of vertices in some graph. Right.
I don't know whether that's right, because there's a locality condition. As you derive the diffusion equation in kinetic theory, there's a locality condition, right? A particle can only jump to something that is, the whole point is, a particle only jumps to what's nearby. And the amount of stuff that can jump to what's nearby depends on the density of particles that, are near that point, so to speak. So my question is, what's the analogous state space?
Just like with a graph, the rules we use are only ever local. The fact that locality doesn't happen to correspond to a spatial locality in all cases is irrelevant. All that matters is ultimately you have a probability distribution and the measure is preserved. You have a continuity equation over the measure.
Okay, what is the measure in that case? So in the case of, I understand for particles, what's that?
The volume measure.
The geodesic ball volume measure or some other volume measure? Because that's not necessarily, I don't see why that's conserved. I mean, the volume that, the total number of nodes in the graph, you could make that be conserved. I don't understand why the local volume measure is conserved.
So, okay, so, right. So like in all of the stuff I've written, right, when you actually derive a continuum probability measure from the graph dynamics, you are taking effectively an average over geodesic ball volumes at a particular vertex, averaged out over infinite time. Right, you have some update rule, you evolve the thing indefinitely, and you take an average out over over all the volumes. Yes. So that gives you a probability distribution over the hypergraph, and the condition of weak ergodicity is equivalent to the condition that probability distribution, that probability measure is conserved.
Indeed.
So why is it not clear that it's conserved? Are we dealing with non-ergodic?
No, but you just said you're looking at it over infinite time. So right. The usual derivation of the diffusion equation does not do that. The usual derivation of the diffusion equation, it's a time-dependent equation, and you're asking, yeah, go ahead.
Exactly, which is why, for instance, at the winter school, I suggested that project about comparing continuum limits, right? Comparing the continuum limit that we use in the derivation of the probability measure, which is an infinite time limit, with, say, the infinite density limit or the infinite geodesic ball radius limit.
Okay, but let's unwrap what you were just saying. Okay, so we've got this graph. It has some, it has geodesic balls in it. We understand what those are. And we have some dynamics for that graph. And then what quantity do you think is conserved? Because as soon as we have
measure,
what's that?
The measure is conserved by definition, because it's constructed so as to be conserved.
But what is the relationship between your measure and this V of R quantity?
Well, the V of R is what yields the measure in in some appropriate limit. In this particular case, for the ergodicity proof, it's it's an infinite time limit.
So does that mean that V of R is conserved?
No.
Why not? So what function of V of R is conserved?
The time average.
But there's nothing to conserve then, because what the conservation is with respect to time.
Right. So it's defined so as to be conserved.
Okay, we've got V of R. Actually, we've got V of R and T. Right? Time varying V of R. The thing is flapping around. You're saying that for a particular R, you are normalizing V of R or something so that it is unchanged? I don't quite understand as a function of T.
So imagine you pick some time cutoff, right? We have some finite amount of time from 0 to capital T, or 0 to tau. Okay, I average out V of R of T for a particular vertex. Yes. Over that.
Yep.
The thing, if the evolution is ergodic, and if it's ergodic over over a time scale longer than 0 to tau, then that quantity will be conserved by definition of ergodicity.
Yes, but it's not very exciting. If it's truly ergodic, which we don't really understand what that means for a graph. In other words, if the thing can flap around throughout graph phase space, so to speak, and fills graph phase space uniformly, then yes, I agree. By definition, that will work, but it's also very boring in that case. Right? It's not ergodic in the sense of populating all of graph phase space equally. Better not be, because our universe doesn't seem to work that way. It doesn't populate all possible graph configurations equally.
But there's nothing that says the phase space has to be all possible graph configurations. That will almost never be true.
Okay, what is the definition of the phase space?
Well, I mean, we come back to this problem of we have to figure out what it is that we're assigning axiomatically and what it is that we're deducing observationally, right?
Okay, so look, to me,
phase space to be the set of essentially the symplectic manifold that's generated by an ergodic evolution.
Yeah, I understand. Then you're back to the same thing again. But the operational point is, I mean, to me, there's a fairly straightforward simulation concept, which is you've got a very big hypergraph. It's got some evolution rule. At the beginning, you measure its dimension, which you can, and yes, there are weak cutoffs that you have to worry about in measuring the dimension. But assume the thing is big enough, those cutoffs don't matter, right? Then you let the thing evolve. It's going to change its dimension, right? That is what these things do. The question is, is there a characteristic way in which it changes that dimension that depends on very little of the detailed dynamics of what's going on? In other words, like diffusion, where it doesn't matter whether the molecules are this shape or that shape, it only depends on, as a result of essentially central limit theorem type results, it only depends on, as soon as there's some level of randomness, the details don't matter in the large scale version of diffusion. So the question is whether a similar thing is going to be true when you have a large enough hypergraph that is being updated according to some rule, where we believe that rule has the same effect as doing certain kinds of random updates. I mean, this to me is a pretty well-defined question.
And no, absolutely, it is completely well-defined. That question is completely well-defined. It's just that none of the things we've done are answering that.
Well, look, in a perfect world, we would have an absolutely giant hypergraph that we would then look at the various evolution rules for it, and we would ask, how does that cause the effective dimension of that thing to vary, right? And we started looking at that using these various approximations in which, for example, the effect of the rule was simply to remove edges, which may or may not be a correct assumption. But let's assume that that's, if we do that, we can ask what happens to the effective dimension. And we seem to have a partial answer to that question. But
right, but as soon as edges aren't conserved, then it ceases to be a well-defined question for the reasons that I've stated.
I'm sorry, what? Well, then our approximation is a bad approximation. I mean, that's the look. A better approximation is the rule just moves around the edges, doesn't delete them, but it might be sufficient
because at least then you wouldn't be monotonically changing the graph radius in such a way as to make the problem ill-defined.
Okay, so last time we started off thinking
what you've got is if you want to think about it physically, what you've got is a space in which your whole notion of distance is being modified, right? Because the ratio of the graph radius, something like the Hubble radius, to the characteristic curvature scale, the thing you're actually using to measure the dimension, is changing as soon as you're modifying the edge count and therefore the graph radius.
Well, I mean, it's a little bit more complicated than that, right? Because the fact is, as we can see, when the edge density gets low enough, the graph radius goes to infinity. When the edge density is high, the graph radius is also smaller. Right? As the edge density goes to infinity, the graph radius goes to 0.
Yeah, right. Which means that the cutoff, the geodesic ball radius, the characteristic curvature radius, also has to go to 0 in order for your continuum limit to be well defined. Which is why, as I keep saying, it matters greatly how these two different cutoff scales interact. And right now, everything we've done here has just kind of completely neglected the subtleties of that interaction. So I don't see.
But again, the thing that we want to do, okay, the case that we're interested in is an intermediate scale between the elementary length and the Hubble radius, basically.
Right. And also, more crucially, the actual dynamical system that's being investigated is not one that is going to monotonically increase or decrease the...
I agree. We started doing that as a first approximation to what was happening. And it may not be an adequate approximation.
I don't even know what it's approximating, because you're computing a completely different quantity, right? You're computing this thing where the cutoff scales are covarying in this weird way.
Okay, well then an alternative would be to say you make these local moves in graph phase space based on sort of local updates in the graph. We can certainly do that. We had specific rules we were going to do that with. The last time we were about to do that, and then we decided we should try the simpler case of just deleting edges, because we thought that the effect of, and perhaps incorrectly, we thought that the effect of making these local changes would be similar to the effect of deleting edges. So maybe that's incorrect, right? You're saying that, rearranging edges.
Well, I thought the original justification was the deleting edges. We were trying to, as an initial stab, we wanted to understand, how essentially would dimension cooldown work in the very early universe, in which case that is a reasonable approximation, but again, has many subtleties associated with how these two limits, commute. If you want to know as a more general dynamical systems theory question, what is the effective theory of, continuum dimension as a consequence of hypergraph rewriting rules, then, it matters whether those hypergraph rewriting rules conserve the number of hyperedges or increase or decrease them, right? And
I think we don't actually know whether it matters, but it might matter. I mean, it matters to the...
How could it? Okay, so in the case where the number of hyperedges is conserved, then in a sense, it doesn't matter how these two quantities interact with each other.
Which two quantities? We've got three scales. We've got the scale you're at, we've got the elementary length, and we've got the Hubble scale.
Right, but because despite me asking for it, because we still haven't completely defined how it is we're planning to measure dimension, we don't know whether the dimension cutoff that's relevant is the one that's at the intermediate observer scale or at the Hubble scale.
Oh, look, we clearly want to measure dimension at the observer's scale. What happens at the Hubble scale is quite invisible to us. I mean, it might not be invisible in the early universe, but
why is that clear, given that many of the dimension probes, are involved in early universe cosmology, where the Hubble scale is what's relevant? It's just an assertion that I don't.
Well, because I think to get a continuum theory, we don't want to be looking at, the continuum theory of a gas is the theory of the bulk of the gas, not how it's contained within your, box. The question is there a continuum theory of the bulk of the early universe? Or is the only theory of the early universe one that depends on the size of the universe? Could be that there is no theory. It could be that there isn't a continuum theory. I mean, it's just like asking the question, can you do thermodynamics for self-gravitating gases? Answer, probably not really, because they eventually turn into black holes, and it matters that they're a discrete set of black holes. So that's a case where the continuum limit doesn't really exist. And this might be a similar one, or it might be, as I rather more suspect, that there is a meaningful continuum limit, and that in the end, there will be an equation that basically just gives you dimension as a function of time.
Sure. But I mean, exactly the same objections that I'm raising would also apply in the gas case.
Which objections?
The objections that we need to define what limits we're taking and what limits we're not taking.
Yeah, the only problem in the gas case is that
derive continuum gas dynamics from molecular dynamics, but we had a varying box size, and we had a varying particle size, and we had varying particle count, and we weren't defining what the relationship between those quantities were, then it would be impossible to deduce anything from that. And that's exactly the situation we're in right now. We have to define what limits we're taking, and what quantities we're fixing, and what the relationships between these quantities are. Otherwise,
okay, but in any given simulation, we are defining that perfectly well. In the case of, the part of the reason I'm pushing back about this thing about limits is that I full well know that in the gas case, if you try and nail this all the way down, it is basically undoable, right? You can do it in simulations easily enough, but if you want to do it in a completely formalized way, I think we finally resolved how to do that, but it involves a whole bunch of heavy lifting that, is still not completely in traditional mathematics well defined.
Right, so but at least with gas dynamics, you have experiments that you can compare. This is, it's kind of what I was saying earlier, right? That at least there you have some robust observations you can compare against.
I know. So this is a scarier case. We're actually trying to do theory.
We clearly don't have an anchor in experiments. So the best we can do, I think, is to have an anchor in mathematics. And to do that, we need to define what it is we're doing.
Okay, well, then in that case, my definition is we get a very big hypergraph. We compute dimension at an intermediate scale between the elementary length and the size of the whole hypergraph. Okay. And we look at the evolution of that as a function of basically time and in step count in some generational step count, I guess. Not super happy with that. We look at that and we simply ask, how does the dimension change as we evolve the hypergraph?
Right. Okay, that's a much better defined question. Right?
That was the question that I started with last Thursday. That was the question I wanted to answer. Then the idea was to find approximations to that, which might be more tractable.
But everything you've been doing so far has nothing to do with that, right? Because you haven't the cutoff radii you've been using have been based neither on the intermediate, are not based on some intermediate scale between the discretization cutoff and the Hubble.
But the cutoff scale, if we have V of R, there is no cutoff scale. V of R is well defined for all R. It might be not useful to treat it, to take account of it in doing a dimension computation, but there is a well-defined V of R for every R.
Absolutely.
Do you agree?
which is why, in order to define what it is we mean by dimension, because this is a function that's defined for all r, we have to specify which values.
Of course. That's why I keep on emphasizing, let's compute V of r, right? So if we compute V of r, so, okay, the well-defined computation, we were doing an El Cheapo computation here, where we're simply deleting edges, which you're arguing is not a realistic computation, and you might be right. I don't know. You're saying, but we can certainly do the more realistic computation.
We have to be careful if we're now changing one of the parameters, and without really,
right.
as far as I can tell, without caring what effect that has on the other parameters.
Okay, so as has happened often in this project, trying to find the simplified case can potentially lead one into trouble, because the hypergraph does what it does, and it's all well defined, and we can certainly compute that, and that's what we were going to do last Thursday, actually. Then look at the variation of V of r as the hypergraph evolves. And I think I've looked at this. I looked at this a bunch like a year ago. And I think I need to go here, but oh gosh, I'm blew through another meeting that I need to do. Well, okay. All right. I think we should wrap up here, but it's a little frustrating. I think we're back to the, we understand what we need to do. I had hoped that we would get more of a clue about what this continuum equation would look like by thinking about these approximations. You attack these approximations on the grounds that you don't know whether they're valid, and I also don't know whether they're valid.
Well, it's not just I don't know whether they're valid. I don't even know what they're computing, right? Because it doesn't seem to me that the quantities that we're getting out are actually well-defined quantities. I mean, well, obviously the volumes are, but it's not clear at all what the significance of those volumes are in the absence of a dimension computation.
Fair enough. Well, to be continued.
The approximation where we were removing and adding edges seemed like it might be a better one, because at least then we're not obviously changing one of the parameters.
I don't know why we're bothering. I mean, we could just run one of the rules, and then it just does what it does. And we can try different rules and see what happens. I mean, I remember that I did look at this like a year and a bit ago, and I probably have some pictures even of what this does. Let me just look for 1 second, and then we really need to wrap up. Let's see whether. I know I had a computation of V of r. These pictures are just a little bit too small. Okay, that's. Yeah, well, I think I had looked at this. I remember some picture of V of r as a function of time. Well, I'm not sure here. Okay, well, anyway. All right, well, there is a definite path here, and I think it's sort of interesting, but I think we're all thinking about
I mean, it's also a strong argument for considering other dimension estimators, right? Something like the spectral dimension or indeed even the Meyer dimension doesn't have a dependence on scale like this one does. So many of these go away.
Okay, well, that'd be interesting to look at.
Or even the random walk. Well, I know this is kind of equivalent to the spectral dimension in lots of cases, but the random walk dimension is also one of these things that's a kind of, doesn't have the same free parameter problem at this particular.
I think they're all going to end up with that. I think it's all going to be equivalent in the end. I think they'll have some implicit dependence of the same kind, because I think that it's really a question of, you imagine. I mean, yeah, at a very small scale, when things are close to discrete, or at the scale where the whole system is being included, I mean, nothing's going to get you out of that. You're going to be able to smear it out in this way or that way. And yes, you'll be able to do some transform effectively, where maybe you can have the effect of that be less obvious, but I doubt you'll get rid of it. I think you have to.
That's not really how dimensions work, right? I mean, like the Hausdorff dimension is scale dependent, but the topological dimension is scale independent.
Yeah. Well, anyway, that would be my guess, is that you won't get something for nothing there, but maybe I'm wrong. All right, have to run along here. Okay, I think we went off in slightly the wrong, along the wrong geodesic here, but it's a shame. But anyway, we got some nice pictures, I suppose. Good. Okay, to be continued. And thanks to a few comments on our live stream here.